Testing. 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 Come on, testing. Why isn't this one working? Testing. Come on, testing. Okay, looks like the volume's on. Happy Thursday, everyone. Welcome to another Hupo stream. We're going straight into the paper world today. 1st of June, 2023. This paper is fresh. We're going to be talking about vision transformers, and specifically hierarchical vision transformers. So this is a paper that's coming out of Meta AI, Facebook AI research. It used to be called FAIR, but now it doesn't make any sense because their name of the company is called Meta. So I don't know what they're going to do. They're going to have to call it Mare, but that doesn't sound as cool. So this paper seemed to be popular, and it seems to be pushing the state-of-the-art for image. I don't know exactly what they're doing to measure state-of-the-art. It seems like from these figures it's ImageNet 1K, so I don't know. You would have thought that all the juice that could possibly be squeezed out of ImageNet 1K has already been squeezed out of ImageNet 1K, but apparently they figured out a little bit more. So there is a GitHub for this. Not super discovered yet, but already being used by a couple different organizations here, it seems. And unfortunately they said they were going to release the models, but if we look at this little table here, it says coming soon, so we're going to have to wait to see when they update this file with these links. Seemingly they have a couple different sizes here. The 224 probably refers to the width and the height of the images. 224 by 224 is a very common image size in computer vision. So you can see here they have Hiera tiny, small, base, base plus, large, and huge. And the difference in ImageNet 1K accuracy, you go from kind of 82% to 86%. And actually, why don't we go to our good old papers with code, and let's do browse state of the art, and let's look for image classification. And ImageNet 1K, let's see, ImageNet right here, data set. ImageNet 1K, currently the state of the art is a basic L Lion 1K. That's probably not the one we want. We want, yeah, I guess that is. So state of the art according to this is 91, but over here we're seeing 86. So maybe there's a difference between the ImageNet here and then the ImageNet 1K. ImageNet real. Let's see if we can find the exact one. ImageNet 1K. Better ViT baselines for ImageNet 1K. Image classification. Benchmarks. Show all benchmarks. Control F. ImageNet 1K. What if we just search for 1K? Here we go. VATB 1K. That's not what we want. Okay, so either this ImageNet is not the same, which it could be. I think there's different ImageNets, but 86 is what they're reporting. And they're reporting the speed on an A100, which kind of lets you know that Facebook is still using the A100. So, you know, little sneak peek there. No one has the H100s. The H100s are the cool kid GPUs, but so far we haven't seen them in any papers. So waiting for that. Floating point 16 is the data type. This is the precision that they're running it at, and the fact that they're giving you the speed in an A100 floating point 16 probably lets you know that that's what they're using for production models. You know, people aren't going to tell you what they use for production models, but you can kind of just intuit based on the stuff that they tell you. Cool. So let's just get into the paper and see what we get. ¿Cómo se llama? Si bonita. Si hiera. Hiera. Yes, that is Shakira. That is a Shakira song. And hello, Nisio. Alright, so let's get started. Modern hierarchical vision transformers have added several vision-specific components in the pursuit of supervised classification performance. Yeah, so this is kind of the tail of the tape for kind of architecture, or really any papers that are trying to push state-of-the-art, is sometimes they just kind of keep adding extra modules, extra crap, extra components that add more priors, more constraints, and pushing the state-of-the-art by just adding more complexity. And I would say almost 80% of papers are doing this. Very few times are people actually reducing the complexity in order to push the state-of-the-art, right? The transformer was one of the fundamental papers that did that, where they found this significantly simpler and less complex model architecture that actually performed way better. So usually you have to add complexity to get better performance, but whenever you figure out a way to remove complexity and get better performance, the whole world is pretty happy with that. So let's see. With these components, while these components lead to effective accuracies and attractive flop counts, the added complexity actually makes these transformers slower than their vanilla ViT counterparts. Not only does it make it slower in terms of inference, but you're now introducing complexity in terms of the actual CUDA kernels and operations that are required to run this. You're adding extra complexity in terms of every single time anybody tries to use it, now they have to understand all this extra complexity. So complexity is bad in a million different ways, so simplification is way underrated. In this paper, we argue that this additional bulk is unnecessary by pre-training with a strong visual pretext task. MAE, this is masked auto-encoding. This is what it looks like. So masked auto-encoding is whenever you take a data set and you take individual pictures from that data set and you basically zero out or mask, right? Masking, like covering. You cover parts of the input and then you basically try to reconstruct the missing pieces, right? So it's very similar to a masked text prediction task where you would take a sentence and then you would zero out certain words in the sentence and you would get the transformer to figure out what the missing words are. So you can basically do the same kind of idea with images, and this is a very popular pre-training task, and the reason is because you don't need labels, right? It's a self-supervised task. For any given image, you can create a input and a target, and it's also like it creates kind of a natural type of data augmentation because you can randomize this masking, so you're going to get a lot of kind of examples out of one single image. So very popular pre-training task. We can strip out the bells and whistles from state-of-the-art multi-stage vision transformers without losing accuracy. In the process, we create Hiera. That's the name that they chose. I don't know about, I would have called it HIT, or something like that, HVIT. I feel like Hiera is kind of a weird, I don't even know how to pronounce that. An extremely simple hierarchical vision transformer that is more accurate and significantly faster. I mean, that sounds really good to me. I don't know about you guys. That sounds perfect, both at inference and during training. We evaluate Hiera on a variety of tasks for image and video recognition. Okay. So beyond ImageNet 1K, our code and models are available at... so this is a lie, of course. They said the models are available, but they are not. Coming soon. We'll see if they ever actually come soon. And another thing here, let's see. Yeah, unfortunately, this is CC by 4. So this license is attribution. So when you see attribution in a license, it means that anytime you use it, you have to basically cite this paper and you have to cite them, which is fine. I don't mind attribution. But then the part of this that sucks is non-commercial. So you can't use this for your startup. You can only use it for research purposes, which kind of sucks. So you can use this for research as long as you tell people that you used this exact thing and you attribute it to them, but then you cannot use it for your startup. So a little bit unfortunate, and of course the models aren't even there, so models being available is a lie. Since their introduction by Dosovitsky a few years ago, vision transformers have dominated several tasks in computer vision. I don't know about several tasks. I think vision transformers are the go-to kind of vision encoder and model architecture. Make them a popular choice today. Moreover, their simplicity unlocks the use of powerful pre-training strategies such as MAE, right? You can pre-train with masked autoencoding, which makes ViTs computationally and data efficient to train. However, the simplicity, what do they mean by data efficiency? Well, you're getting a lot of kind of juice out of a single data point, right? Just one picture can result in basically thousands of potential training examples, right? Because think about how many different permutations and combinations of missing masked tokens versus revealed tokens you can create just from one example. So it's like a form of data augmentation that's kind of baked in to the task itself. This simplicity comes at a cost. By using the same spatial resolution and number of channels throughout the network, ViTs make inefficient use of their parameters. So this is kind of the argument for hierarchical, right? Obviously, they're going to be promoting the hierarchy and the kind of benefits that you get from having some prior that gives you a kind of a multi-scale, right? Big version of the image, smaller version of the image, even smaller version of the image, right? Multiple scales, hierarchies of scales, which use fewer channels but higher spatial resolution in early stages, and more channels but lower spatial resolution in later stages. And this is what convnets do as well, right? In a convnet, the number of channels at the very beginning is basically 3, right? Because you have 3 channels in an RGB image, right? But then as you go deeper and deeper in the convolution network, the number of channels actually increases, right? So you see here it's the depth, which is the number of channels in this picture. So here, the depth at the beginning would be 3, and then by the time you get to the end, it's going to be something like 256 or 64 or some deeper amount of channels. But they no longer represent red, green, and blue. They represent kind of abstract concepts. Several domain-specific vision transformers have been introduced that employ this hierarchical design, such as SWIN or MVIT. Okay, so it's not the first time that people do hierarchical vision transformers. Other people have tried. You got some 2021 papers here. However, in the pursuit of state-of-the-art results using fully supervised training on ImageNet 1K, fully supervised training on ImageNet 1K, so this is if you were to take ImageNet 1K, which is just basically here's a picture and then here's the category that it corresponds to, and the 1K on the ImageNet there, it means is 1,000 categories in ImageNet. So things like dog, cat, airplane, car, there's 1,000 of those, and then it's basically a 1,000 category classification problem. And fully supervised training on ImageNet 1K would basically mean that you're taking this picture and the target would be dog, right? So for every picture, there's a target, and the target is basically a specific category. These models have become more and more complicated as they add specialized modules. So CS-Win had crossed shape windows, some kind of fancy position embeddings, and MVIT v2. While changes produced effective models with attractive floating point operation counts. Okay, so how many floating point ops, how many flops does your inference take? Under the hood, the added complexity makes these models slower overall. Yeah, and it doesn't just make it slower computationally, it makes it slower for research and understanding purposes as well. This bulk is actually unnecessary. Hard agree, because ViTs lack inductive bias after their initial patchify operation. So once you cut in a ViT, right, you're cutting up the image into these patches and then you're basically feeding that in, right? So at the very first layer, there's this kind of bias that you're basically saying left to right and top to down. You're basically saying the ordering of these tokens matters because I put them in a specific order of left to right and top to down. But then as soon as you get to the second block of the transformers, because the transformer can basically, anything can pay attention to anything, you lose that kind of like bias of like the patch order. So Many of the changes proposed serve to manually add a spatial bias. Okay, so basically other times that people have tried to add complexity to improve vision transformers, they're trying to add back that spatial bias into the architecture, right? And convnets have spatial bias constantly, right? Because in a convnet, the multiple layers of the convnet, they're constantly redoing this convolution operation, right? Convolution GIF. Let me see if I can find this GIF. I love this GIF. This one. Right, so the convolution constantly does this. The next layer after also does this. The layer after that also does this. So at every single layer of a convnet, you're basically introducing this spatial bias. Versus a vision transformer does not have that. A vision transformer has this spatial bias at the very first layer, but then as soon as you get to the second layer, the third layer, the fourth layer, it loses that spatial bias. So what they're saying is that people have tried to kind of figure out a way to add that in there. But why should we slow down our architecture to add these biases if we could just train a model to learn them instead? In particular, MAE pre-training has shown to be a very effective tool to teach ViT's spatial reasoning, allow pure vision transformers to obtain good results on detection, which was a task previously dominated by models like SWIN or ViT. So why would MAE pre-training result in some kind of spatial bias? Because the information is mostly blank, right? It's like because you have a bunch of blanks and then you have information only at very specific points, the blanks kind of act almost like as a form of letting the model know this part is empty. This part, of course, this empty part here is also the same empty part here, which is also the same empty part here. So like, I could see how it's kind of propagating that spatial bias deeper into the vision transformer. Which was a task or whatever. MAE pre-training is sparse and can be 4 to 10 times as fast as normal supervised training. So why is it sparse? Because most of it is empty, right? Sparse just means empty. Making it an already desirable alternative across many domains for more than just accuracy. DR, cool. What's the cool with respect to DR? We test this hypothesis. We're going to come back to this figure. Let's just finish the introduction here. We test this hypothesis with a simple strategy using some implementation tricks. Take an existing hierarchical transformer or hierarchical ViT or ViT. I've seen people call them ViTs in podcasts, but I don't know where I started pronouncing it as ViT. I think obviously like my pronunciation comes from somebody else pronouncing it, but I forget who I heard pronounce it first. So I don't know. Do you guys think it's ViT or do you guys think it's ViT? Do you guys use ViT or ViT? Carefully remove non-essential components while training with MAE. After tuning the MAE task to this new architecture, we find that we can actually simplify or remove all the non-transformer components while increasing in accuracy. Dude, big win right here. This is what I want to see. We made it simpler and it made it better. You know? That's what life is about. It's about finding simple solutions that work even better. The result is an extremely efficient model with no bells and whistles, no convolutions, no shifted or weird cross-shaped windows, no decomposed relative position embeddings. Just a pure, simple, hierarchical ViT that is both faster and more accurate than prior work. Damn. You know what I'm thinking about? I'm thinking about the I just want to be pure. This is a meme from, I guess I should... This is a really deep cut, but this is like there's a funny TV show here in America, and that's a famous scene from it. Our simple hierarchical vision transformer outperforms state-of-the-art on images that far exceed prior work on videos while being much faster. All right, I don't know about you guys, but I'm excited now. This introduction, it's got me hooked. I'm hooked on this paper. All right. Hiera setup. Modern hierarchical transformers like the SWIN transformer or the MViT are more parameter efficient than vanilla ViTs, but end up slower due to the overhead from adding spatial bias through vision-specific modules like shifted windows or conv. Right? So this problem of like having to reintroduce that spatial bias by adding all these extra little bells and whistles throughout the actual model architecture. In contrast, we designed Hiera to be as simple as possible. To add spatial bias, we opt to teach it to the model using a strong pretext task like MAE. Okay, so you're not explicitly adding that prior in the sense that you're putting it in the model architecture design. You're adding that prior in the form, in the way that you are training it via the task, which is kind of a powerful concept as well, right? Where you don't necessarily need to create a model architecture that has a specific prior. You can basically induce a specific prior via the task itself. I wonder how many other different areas of ML could also benefit from that kind of mentality or idea. Hiera consists entirely of standard ViT blocks. Okay, so I guess just all of these blocks here are ViT blocks. For efficiency, we use local attention within mask units for the first two stages and global attention for the rest. So local attention versus global attention is basically how much of the sequence do individual tokens have access to. Let me pull up a thing, but first, at each stage transition, Q and the skip connections have their features doubled by a linear layer and spatial dimensions pooled by a 2x2 max pool. Okay, so what do we mean by local versus global attention in transformer? Okay, so this is not a transformer, but this is a fully connected neural net, but I think it kind of shows you a good idea of what's going on here. So in global attention, this little neuron here can pay attention to every single neuron in the layer below, right? But local attention, it's only paying attention to the local neurons kind of directly underneath it. It doesn't really make any sense in this context of a fully connected neural net. This is more what you should be thinking about, because this is a vision transformer, so this is a transformer attention map, right? Every part of the patch is paying to every part of the every patch in the image, which is sometimes I call the patch a token because transformers in the NLP world are dealing with tokens. Here they're dealing with vision patches or image patches, right? So every single one of these patches, if you had global attention, they can pay attention to every other patch. If you have local attention, you're constraining it to only the tokens that are kind of near it in the sequence. So that's global versus local attention. We got skip connections. So skip connections, ResNet skip connections. Skip connections in a model architecture are whenever you basically take the output of one layer, and rather than feeding it just to the next layer, you actually make it skip a couple layers, right? Skip layers and then come up to a part of the neural network at a later point, right? And these skip connections are very popular. You pretty much see them everywhere, and they solve some things like the vanishing gradient problem. They also make things easier to train. They also kind of, in a way, are a form of kind of hierarchy, if you want to think of it that way, because it gives layers at the top a representation of low-level features, mid-level features, and then high-level features. Okay, we got spatial dimensions pooled. So we've explained pooling before, but pooling is basically when you reduce features by basically picking the maximum, right? So max pooling is best explained with pictures such as this, right? So in a max pooling, let's say you had the layer before you had a 4x4 grid of numbers. When you max pool it, you basically say, okay, well, rather than passing all four of these numbers, that's too many numbers. I don't want to deal with all these numbers, so I'm going to instead pick the maximum out of all these four, right? So the maximum here is 9, so I'm just going to pick 9. The maximum here is 7, so I'm just going to pick 7. And why does this even work? And the reason it works is that generally a lot of what's happening inside a neural net is basically you're getting these outliers. We saw that with the quantization papers that we were reading, where basically most of the time, most of the numbers are basically very close to 0. They're not really giving you anything beneficial. Usually there's a small amount of neuron activations that are actually outliers, and they're very strong, and those are the ones where the actual signal's coming through, right? That's where the intelligence is actually propagating through the network, is through these kind of very large outliers that are appearing, right? very large activations. So when you max pool, you're basically saying ignore all the activations that are very tiny and I don't care about. I only care about the kind of outlier activations here. So there's different types of pooling. There's average pooling where you would take the average of that, but max pooling is the easiest to do because if you average pool, now you have to do an average, right? You have to spend time computing the average of all these things. If you max pool, it's very easy and quick to do what is the maximum here. All right. So let's actually look at this diagram here. You have a target. This is 1, 2, 3, 4, 5, 6, 7. Kind of a weird number of patches there, but I don't think this is the real number of patches that they use. I think this is just for the figure, just for visualization purposes. So they're cutting it up. They're feeding it into patches. But interestingly here, it's not like they have the empty tokens in the patch. They only have the ones that contain content. So usually if you're going to do this, you have to have some kind of notion of position embeddings in here, but like here they're literally just showing you the patches that actually aren't empty, and somehow those are being fed into here. All of these are just going to be basically transformers. Every single one of these is a transformer block. I guess with this crosshatch pattern you have the pooling, so notice how the pooling occurs once you reduce the dimensions here. So these two transformer blocks are going to be much wider, much more numbers of parameters, and then in order to kind of reduce down the number of parameters, you see these pooling operations, right there, right before it reduces the width, right? And here you have global attention. So once you get to the higher level features, you can do global attention, but at the low level, with the low level features, you're just going to do local attention, which I think is what they meant here. And obviously this is a auto encoder, right? And in an auto encoder task, you have an encoder and a decoder, and right here, this little representation that is getting passed from the encoder into the decoder, that's going to actually be usually what you use for your embeddings. So whenever they actually do ImageNet 1K classification, they're probably only going to use this encoder, and then they're going to take this very last layer here, and then they're going to add a little classification head on top of that, and then do a classification task with that. So this decoder here, they're probably not really going to use that for the benchmarks. Related works. There's quite a lot of spatial bias in the mask unit attention they use. Bit misleading introduction. Okay, interesting. So they're shitting on the fact that other people try to put spatial bias in it, and then they figure out a way to put spatial bias in it, but they don't tell you that it's a way to put spatial bias in it. They use local attention. Yeah, I agree with you. Local attention is kind of a form of spatial bias, right? Because in a local attention, you're kind of letting you're making the tokens only pay attention locally. So that is a form of spatial bias because you're saying this stuff shouldn't matter, this stuff should matter, right? So as soon as you say the stuff around you matters more than the stuff farther away from you, that is a form of spatial bias that you're introducing into the model. So I agree with you that local attention is a form of spatial bias. MAE always only includes the non-mask tokens in the encoder. Okay, so it's always the non-mask tokens. They never include the mask tokens. Good to know. Vision transformers have attracted attention because of their massive success on several vision tasks, including image classification, video classification, semantic segmentation, object detection, video object detection, 3D object detection, 3D reconstruction. Okay, so they're just like literally listing every single type of vision task that exists. The difference between vanilla ViT and prior convolutional neural nets is that ViT partitions images into a 16 by 16 pixels, aka patches, and flattens the spatial grid into a 1D sequence. Right? And that's how you can feed it into a transformer, because the transformer just consumes sequences. Whereas CNNs maintain this grid over multiple stages of the model, reducing the resolution in each stage and introducing inductive biases such as shift equivariance. So what is shift equivariance? Shift equivariance is the fact that something that's like a dog in this part of the image, if you shift it and you put the dog in this part of the image, it should be the same. So basically there's this kind of equivariance bias in a convnet that's saying that no matter where this dog is within the image, it's still a dog, right? This feature, no matter where it is in the image, it's still going to be that feature. Recently, the field has shown an increased interest in hybrid methods that combine transformers with convolution-like operations in the hierarchical stage structure of prior CNNs. This direction has shown success and achieved some state-of-the-art on various vision tasks. However, in practice, these models are usually slower than the vanilla ViT, and convs are not easily compatible. And another thing to think about is that not only are like convnets or are these kind of hybrid models slower than a ViT, but as we progress, I'm pretty sure that the hardware is going to become much more specialized for transformers. Think about all the startups and all the people at NVIDIA that are designing hardware. They're designing hardware for transformers at this point, right? Everybody's kind of agreed that transformers are the future. So the more that transformers become popular, the more that hardware is designed specifically for transformers, and then the more that anything other than a transformer becomes worse. So it's not just that they're slow now, it's that they're going to be slow in the future, even more so, because people are going to overfit to the transformer architecture when it comes to hardware design. Convs are not easily compatible with popular self-supervised tasks such as masked image modeling. We address both of these issues in the creation of Hiera. Masked pre-training has emerged as a powerful self-supervised learning pretext task for learning visual representations. So what do they mean by learning visual representations? So this little last layer here is what they're referring to when they call it a visual representation, right? And it's a representation of this image, right? It's a compressed form of this image. It's like this image is some point in a very, very high dimensional space, which is the space of all images. This little vector here is also a point, but now the space that that point lies in is much smaller. It's a compressed space, right? So that compressed space is going to be useful for a variety of different things, right? Whether it's classification, whether it's segmentation, whether it's detection, whatever you want to do, right? And that's kind of a magical thing as well, right? It's kind of magical that you can use a pre-training task and result with a encoder that gives you a representation that is useful for a bunch of downstream tasks, right? That kind of transfer learning that we just kind of take for granted is huge, right? Among previous works, Luke Byrne. Positional information is stored inside the token itself via the positional encoding at the start. This means that after the position embedding, you can randomize the order of the tokens with no effect. Yeah, they haven't mentioned position embeddings, and then they actually shit on the position embedding. So yeah, they were like, oh, this is bad, relative position embedding. So as far as we have gotten in this paper so far, we don't know if they actually give position embeddings. They probably have position embeddings, but let's wait to see them actually mention them before we assume that they have position embeddings. Allow any length input and thereby derives an efficient training regime using the sparsity of masked images. So again, if you have a lot of empty parts of the image, it makes the actual computation in the training process easier, right? There's just less chain rule, less backprops to do. This greatly improves the training efficiency of mass pre-training, but adapts sparse training to hierarchical models is non-trivial because the input is no longer laid out in a rigid 2D grid. There have been several attempts to enable hierarchical ViTs and to use mass pre-training. Mask feet SimMim replace masked patches with mask tokens. So here, this empty here, there's a specific token for that. It's called the mask token, meaning most computation is wasted on non-visible tokens and training is incredibly slow. Introduce several techniques to enable sparsity in every component of the network, in the end creating a much more complicated model that doesn't improve much in accuracy. Ooh. little diss on Huang et al. Here. UMMAE uses a special masking strategy that allows for sparsity, but this restriction significantly hurts accuracy. MCMAE uses a masked convolution in the first couple of stages, which obtains high accuracy, but significantly reduces the efficiency of the model overall. We bypass all of these complicated techniques and restrictions by designing our architecture specifically for sparse MAE training, pre-training, therefore creating a powerful yet simple model. Okay. So, I mean, so far they've just kind of said the same thing 10 times, right? They just kind of Let's actually look at this figure. Performance versus prior work. Hiera compared to B, L, and H variants of the SOTA model. So this is state of the art, and then these are different sizes, so big, large, and huge, that use MAE like pre-training. On images, Hiera is faster and more accurate than even the most recent state of the art. Look at that. They got some 2022 papers and then a 2023 paper, offering a 30 to 40% speed up, which is fucking huge, compared to the best model at every scale. On video, Hiera represents a new class of performance, significantly improving accuracy while being over 2x faster. 2x faster, significantly improving accuracy than popular ViT models. Okay. So here we have two plots. We have on the left, we have an ImageNet 1K accuracy. This is probably top 1 accuracy or top 5 accuracy. And then here on Kinetics 400, this is a video benchmark. So accuracy on video, accuracy on image classification. And here you have inference speed in images per second, and then inference speed in clips per second. So comparing with vanilla ViTs and then a couple ConvNext V2. This was actually we read this on the channel as well, the ConvNext paper. But you can see obviously the bigger models are going to get higher accuracy. That's what these dots at the top of the line represent. And then the smaller models are going to get lower accuracy, but they're going to be faster. So you always kind of generally have this kind of like expanding curve like that. So Hiera, the best Hiera model is faster, but not more accurate than the best ViT. So you see the biggest ViT here is pretty much just about as accurate as the biggest Hiera model, but the biggest Hiera model is actually faster. And all of them are faster. And actually, look at this. The smallest Hiera model is not as accurate as the smallest ConvNext V2 and MCMAE model. But all of these are very, very close. So if the y-axis is zoomed in. So if you see this, the difference here is like literally 0.5. So it's not like we're talking about 40% accuracy and 80% accuracy. We're talking about 84.5 versus 85, which is kind of a wash IMO. And it also does much faster on video and seemingly better on video as well. All right, let's go into the approach. Our goal is to create a powerful and efficient multi-scale vision transformer that is above all simple. We argue that we do not need any specialized modules like convolution, shifted windows, or attention bias. Is local attention a form of a bias in the attention? To obtain high accuracy on vision tasks. This may seem difficult as these techniques add a much-needed spatial bias and temporal bias that vanilla transformers lack. So we talked about spatial bias, but you can also have temporal bias, right? Some kind of prior that makes it clear that this thing happened before this thing. Right? So actually, when you think about it, if you think about a sentence, right, is that spatial bias or temporal bias? Because whenever you have a sentence, there's the ordering of the words is actually almost a form of temporal bias if you think of a sentence as kind of a thread of logic over time. Well, prior work adds spatial bias through complicated architectural changes. We opt to keep the model simple. Take an existing vision transformer and ablate it, bells and whistles, while training with a strong pretext task. For the pretext task, we use masked autoencoders, which have shown effectively in teaching ViT's localization capabilities. By having the network reconstruct masked input patches, note that MAE pre-training is sparse. The masked tokens are deleted instead of being overwritten, like in other masked image modeling approaches. This makes pre-training efficient, but poses a problem for existing hierarchical models as it breaks the 2D grid that they rely on. Moreover, MAE masks out individual tokens, which are large 16 by 16 patches, but only small 4 by 4 patches for most hierarchical models. To address both of these issues, we opt to distinguish tokens from mask units. Mask units are at a resolution we apply MAE masking, while tokens are the internal resolution of the model. Okay, so they're going to have two different types of patches here, right? They're going to have patches that are actually being used as tokens, and then they're going to have patches that are how they mask it out. I think that's probably what this figure here is. Yeah, so they're making a distinction here between a token and what they're calling a mask unit. So a mask unit is basically of arbitrary size, and then the token is of the same size. Let's see what they're saying. We mask 32 by 32 pixel regions, meaning one mask unit is 8 by 8 tokens at the start of the network. Okay, yeah, so this is making it clear that the mask token size is going to change, or mask unit. The mask unit is probably going to be different at the beginning than at the end, right, as you get higher and higher in this hierarchy. We can use a clever trick to evaluate hierarchical models by treating mask units as contiguous, separate from other tokens. Thus, we can continue with our experiments and use MAE with an existing hierarchical vision transformer. Okay. MAE is not compatible with multi-stage models, but we can apply some simple tricks to remedy this. While MAE masks individual tokens, tokens in multi-stage transformers start very small, i.e. 4 by 4 pixels, doubling the size in each stage. Thus, we mask coarser units, which they're calling their mask units, which are 32 by 32 instead of tokens directly. For efficiency, MAE is sparse, meaning it deletes what it masks, a problem for spatial modules like convs. Yeah, so what do they keep referring to here is that if you were to try to do MAE with a convnet, you would have to zero out. You would just put zeros here, and then you would end up with a bunch of zeros here, and then you would end up with a bunch of zeros in the next layer, and the next layer, and the next layer, because it's like the way that convolution works, it needs to actually see everything. It's like you can't modify the convolution operational, this kind of striding pattern, right? Versus inside a transformer, you can just not pass in the empty tokens, which is what's happening here. You see how they're not passing in these empty tokens. They're just only passing in the tokens that are not empty at all. So you're not just zeroing out the missing parts, you're deleting the missing parts. Keeping the mask tokens fixes this, but gives up the potential 4 to 10x training speedup of MAE. As a baseline, we introduce a trick that treats a mask unit as separate entities for convs, solving the issue but requiring undesirable padding. Okay, so if they're going to be messing with this mask unit and the token size, they're going to be like changing the size of these mask units and then the token units, you're probably going to end up in some situation where you have to either pad or crop something, right? Because the sizes aren't necessarily going to magically fit every time, right? So that's probably what they're referring to here. We sidestep the problem by changing the architecture so that kernels can't overlap mask units. Okay, so here are mask units. Here's a couple of different problems with mask units. So problem number 1, the masked autoencoding task deletes mask units. So you have 3 units here, and then you delete it, and then you basically just, this is what the transformer is seeing, just these 2. But what are you going to do with this one? This breaks the 2D grid, right? You see this if you were to do a convolution operation over this. The convolution operation, like, what are you doing? Do you have it over that? Because convolution like, you can't just remove parts and then squish them together, because then the convolution is going to be learning something completely different, right? The whole assumption of a convolutional neural net is that the pattern that you're learning here, right, like this kernel is repeated throughout the image, and if you learn it in one place, you can use it pretty much anywhere in the image, right? This is what those little individual things that are being strided like that look like, right? And when you see this like this, it's like, what am I looking at? You see how this is dark, then light, then dark? So these are edge detectors, right? So this is what a primitive edge detector looks like. And people actually used to design these by hand. People would design these edge detectors by hand. And you can see here how this edge is detecting like 45-degree edges. And this one here is detecting horizontal edges. And this thing here is detecting vertical edges. And this thing here is detecting basically like a color gradient. So something that goes from red to green, where the red and the green channels, like kind of the red fades and the green starts. So that's what these like little low-level features in a ConvNet end up learning. And these actually used to be hand designed, which is crazy to think about, called like HAR wavelets. Let me see if I can find that. HAR wavelets. Yeah. So these are like the old school hand designed ones. So you have vertical edge detection, horizontal edge detection, diagonal edge detection. But we don't do that anymore. Now we just basically let the neural net learn these low-level representations. Okay, so, but you have this problem where if you delete these mask units, your convolution is going to be nonsensical. So what are you going to do about that? Okay, so they got 3 potential solutions here. They got mask feet, where, okay, we delete this, we don't delete it, we instead replace it with a mask token. But the problem is that then you're not gonna, it's gonna be not sparse, right? You're gonna feed the entire image as an entire very, very long sequence into this encoder. So it looks like 90% of that is basically just gonna be this mask token, and you're just gonna spend a bunch of time multiplying mask tokens by mask tokens and getting nowhere, right? Just a bunch of wasted compute in training. So that's the problem with this solution. Separate units and pad. Okay, so they're saying, well, what if instead we just do the convolution on each individual mask unit, but now, because the convolution size isn't necessarily going to correspond directly with the size of this mask unit, we're going to have to probably pad these mask units. So now you have additional worthless computation due to the fact that you have all these zeros in the padding, that now you're multiplying all these zeros with all these zeros here, and you're spending a bunch of time calculating the convolution with the padding. You could probably save that, right? So how do they do it? Hiera, just set the kernel size equal to the stride, sparse, no overhead, simple. Okay, so the size of the kernel is here 3 by 3 versus 2 by 2. So what they're saying is, okay, adjust the size of this convolution operation, right? The stride is how many it moves, and then the kernel size is the actual size. So back to our picture here. The stride here is 1 because you see how it's moving 1 at a time. So the stride here would be 1, and then the kernel size here would be 3 by 3. So what they're saying here is make the size of the kernel and the stride match whatever you pick for your mask unit, so that you don't have any padding and you don't have this error here where you have to kind of split it over the deleted token. Message retracted. Nisio, what's going on? Oh, this is a 2 by 2 max pooling, not a ConvNet. Okay, so this is max pooling, which is this. Right? So that's what they're doing. That makes more sense. Thank you, Nisio. The positional information is stored inside a token. Okay. Preparing MVIT v2. We chose MVIT v2 as our base architecture, as it is small. 3 by 3 kernels are affected the least by the separate and pad trick described in Figure 4D. Although we likely could have chosen a different transformer and obtained similar end results. So MVIT2, which is Lee et al. I bet you one of these guys is also Lee. Yeah, it might even literally be this guy. Maybe not. Usually whenever people do that, it's just their previous work. That is, it learns multi-scale representations over its 4 stages. It starts by modeling low-level features with a small channel capacity, right? So at the very beginning, you have small channels, so 3 channels, and then as you go further, you're going to have more and more channels. That trades channel capacity for spatial resolution to model more complex high-level features and deeper layers. A key feature of the MIT v2 is the pooling attention, wherein the features are locally aggregated. Local there because the pooling is inherently a kind of local operation, right? You're pooling with the little neighbors in your little area. Typically using a 3 by 3 convolution before computing the self-attention. In pooling attention, the K and V, so K and V are the key and value matrices inside a transformer attention block, are pooled to decrease computation in the first two stages, while Q is pooled to transition from one stage to the next. So all of these are just big matrices of numbers here. One stage to the next by reducing spatial resolution. MVIT v2 also features decomposed relative position embeddings. Okay, so who was it? Luke, you were saying that they probably use position embeddings. Here you go. So they've confirmed that they're using position embeddings. I guess it made sense that they would probably do that. So they're using decomposed relative position embeddings instead of absolute ones, and a residual pooling connection to skip between pooled Q tokens inside the attention blocks. Note that by default, pooling attention in MVIT2 contain comms with a stride of 1, even if no downsampling is required. Okay. So let's see if this little picture here. So we have our Q, we have our K, and we have our V here. The K and the V are pooled. I think that's what they're trying to say here. MVIT2 uses pooling attention, which performs global attention with a pooled version of K and V. Okay, so global attention is obviously going to be much more expensive to compute than local attention because it's dense, right? Every single part of the sequence is being paying attention to every single other part of the sequence. So if you're going to be doing global attention, that's where you would want to use the pooling, right? So you would want to pool before you do that global attention. This can be expensive for large inputs for video, so we opt to replace this with mask unit attention, which performs local attention within mask units. Okay, so in the local attention, here, right, this one, there's a hyperparameter here where you're deciding what the size of this kind of local attention is, right? Is it 3? Is it 10? Is it 100? Right? Like what are you constraining this local attention to in terms of like how many neighbors can it pay attention to? So the way that they're going to do it is that they're going to use this mask unit. So there's kind of like, it seems like a lot of what they're doing in this paper is like basing all these different hyperparameters, like the stride, the size of the pool, the size of the kernel, the size of the token, right? Like they're basically like having all of those kind of come from one thing, which they're calling the mask unit. And then they're basically by having all their hyperparameters kind of emerge from the one hyperparameter here, which is the size of this mask unit at every single layer, then they can basically make all the math work out clean, right? So there's no padding, there's no extra crap. It's like everything fits perfectly. You're convolving a thing of 8 by a thing that is 2, right? So this has no overhead because we already group tokens into units for masking. We do not have to worry about shifting like Swin because we use global attention in stages 3 and 4. Figure 2, stages 3 and 4. Figure 2. I guess this is stage 2, and then this is stage 3, and then this is stage 4. And then, yep, and then you have the pooling at stage 2, and then pooling at stage 3, and then pooling at stage 4. So this is where you have this pooling, which they're describing here. Mask unit attention. And this is one mask unit. So I think that's what this entire thing is. One token and then one mask unit. So one token within the mask unit, and then the mask unit is the whole thing, which is what they're showing you here. You see how they're keeping it consistent. The mask unit here is basically just the corner of the eye of the dog of the nose, and here it's the same, the corner of the eye of the dog in the nose. So I like that. I like when the figures are consistent with each other like that. Applying MAE, since MVIT v2 downsamples by 2 by 2 a total of 3 times. So downsamples by 2 by 2, what do they mean by that? Well, the pooling is downsampling, right? Whenever you pool, you're downsampling, and they're downsampling 3 times here. Right here, right here, and right here. So that's what they're meaning by that. because it downsamples a total of 3 times, and because it uses a token size of 4 by 4 pixels, we employ a mask unit of size 32 by 32. Right, so if you do everything in these powers of 2 and you're basing your mask unit on the size of the token and the token on the size of the mask unit, and then you're basing your pooling on the size of the mask unit, then it's always going to work out, right? The tokens are always going to be some even subdivision of the mask unit. The mask unit is always going to be an even subdivision of whatever they need it to be for this local attention. This ensures that each mask unit corresponds to 8 to the 2, 4 to the 2, 2 to the 2, 1 to the 2 tokens. I like this, 1 to the 2, in stages 1, 2, 3, and 4, allowing each mask unit to cover at least one distinct token in each stage. To make sure conv kernels do not bleed into deleted tokens, we shift the mask units to the batch dimension to separate them for pooling, effectively treating each mask unit as an image. So whenever you're doing training, right, you have one image. Let's say you're doing supervised training and you're doing one image and then you have one label for that image, right? Generally, whenever you're computing gradients and you're backpropagating, you're not actually doing backpropagation for that one image and that one label. You have a batch of images and a batch of labels, right? And that allows you to basically more efficiently do the backpropagation and get all the gradients and then adjust the weights by those gradients inside your GPU. So what they're doing here is they're shifting the mask units into the batch dimension. So each mask unit is almost like a separate image. And this is not necessarily new. Like something similar happens in a bunch of different computer vision things. Like for example, here in a lot of these old school mask RCNN, which is a kind of a object detection pipeline that then feeds into a segmentation model, you have the same thing where like the first stage of the pipeline is creating a bunch of candidate boxes, and then each of those candidate boxes is being then fed in as if it was a batch of images into the next stage of the pipeline. So this is a pattern that I've seen many times before. Undo the shift afterwards to ensure that self-attention is still global. Oh shit. Okay, so you by separating them into the batch dimension, you're basically, that's almost like a natural way to kind of create the local attention. That's kind of cool. Okay, I'm liking that. In this section, we remove non-essential components of MVIT2 while training with MAE. We find that we can remove or otherwise simplify all of them while still maintaining high accuracy for image classification on ImageNet 1K. So this is their base or their benchmark that they're trying to beat. We use MIT V2L to ensure that our changes work at scale. So what are they suggesting here is like sometimes what happens is if you find a certain kind of behavior with a model that is small, maybe it doesn't actually sometimes work with a big model. Like big models have different dynamics than small models sometimes, even though there's plenty of papers that are showing that more and more it doesn't matter. I think I don't know if we read a paper, but I definitely remember seeing a paper where they showed that you can do hyperparameter tuning on a small model and then use those same hyperparameters on a big model and it still works fine. So even though it's not like fully understood, they're making a point here to say that, hey, we're using this L because we want to make sure that all this hyperparameter that we're exploring, this space of all the different model architectures, we want to make sure that the stuff that we're doing here is not just going to work for these small models, it's also going to work on the big models because we care about the big models. I found the way that they wrote this section quite strange. 3.1 isn't actually what they use in Hiera. They describe a lot of changes in 3.2. What do you mean? So 3.1, they're describing their starting point. So they started from this MVIT v2, right? And the way that they did this paper, they say it a couple times here, is that they basically they start from a more complicated model and then they try to ablate their way out, right? So they're starting from this more complicated MVIT2, and then they're like, okay, well, how many things can I remove from this and then still get the good performance? I'm trying to find exactly where they said that, but yeah, here. We devise a simple experiment. Take an existing hierarchical vision transformer and ablate its bells and whistles while training with a strong pretext task. So I think in this section 3.1, they're just telling you, here's the starting point, and then here's all the different bells and whistles that this starting point has, and then here are all the ways that we removed the things. Yeah. So it's kind of telling a story rather than saying, here's the magical architecture that we came to and don't question how we got to it. Instead, they're saying, here's where we actually started from, and then over whatever it was, months, we basically removed a bunch of things, and then here's where we're going to end up. So they just described where they started, and then this is going to be probably how they got to it, right? The story. So relative position embeddings. Okay, so maybe they do remove the position embeddings. Let's see. MIT V2 swaps the absolute position embeddings for more powerful relative position embeddings added to the attention in each block. Technically, we could implement a version of this that is compatible with sparse pre-training, but doing so would add a lot of complexity. Instead, we opt to start our study here by undoing this change and using absolute position embeddings instead. Okay. So I guess when I said here that they use decomposed relative position embeddings, that's actually incorrect. What they're using is absolute position embeddings. So I can see what you're saying, Nisio, that it's a little confusing. They make it sound like they're doing this, but then they change and they say, no, we actually did this instead. So these relative position embeddings are not necessary when training with MAE. Further, absolute position embeddings are much faster. Okay, so I mean, they don't really give a good explanation why this necessarily performs better, but it does. Is there any intuition here on why absolute position embeddings would perform better than relative position embeddings? I think part of the reason is that they probably keep the images are all the same size. Could that be kind of the thing? I think relative position embeddings, they might be more useful whenever your sequence size is constantly changing. Like whenever you're looking at text, right, the size of the sentence constantly changes in text. So maybe there's kind of some weird relationship there where because there's more consistency in kind of the size of images and the kind of layout of images or something like that, maybe that's why the absolute position embeddings are just as good as or if not better than the relative position embeddings. But I don't know, maybe you guys can try to use your intuition to try to understand why the black box behaves the way it does. Removing convolutions. Next, we aim to remove the convs in the model. Yeah, get rid of these fucking convs, dude. Nobody likes convolutions, which are vision-specific modules and potentially unnecessary overhead. We first attempt to replace every conv layer with max pools. I mean, that's pretty badass, which itself is fairly costly. The result drops accuracy by over 1% to the images, but this is also to be expected. We've also replaced all the extra stride equals 1 convs with max pools, which impact the features significantly. With padding and mask units, this in effect performs a ReLU on every feature map. With padding and small mask units, this effectively performs a ReLU on every feature map. So I think sometimes, like, if you actually look at the Inception ConvNet architecture, so I remember seeing this and it was kind of like crazy when I saw it, but like this is an old ConvNet architecture, but it's probably irrelevant. But like the reason I'm bringing it up is because one of the things that it has is it had 1x1 convolutions, right? And I remember when I first saw this, I was like, dude, what the fuck is a 1x1 convolution? So obviously a 3x3 convolution is this, right? You can see that 3x3 kernel that's getting strided. But like, how does a 1x1 convolution make any fucking sense? Like, what is even going on? What information is passing through here in this 1x1 convolution, right? But it works better. You know, something is going on here. Having that additional weights here that you're learning over time that are only applied to a 1x1 thing makes it better, right? So this always kind of like blew my mind that a 1x1 actually does something, but it does, you know. My guess, relative positions can be learned from absolute embedding. Seems to fit the pattern of reducing hard-coded knowledge, make the temperature architecture more flexible, and let the GPUs go burr. Yeah. So, yeah, it's like there's kind of this counterintuitive nature to machine learning, right? Where it's like you think that by adding more complexity and adding more priors and like adding more theoretical kind of guarantees, like the performance would improve, but like time and time again, right, we get the bitter lesson, which is actually just make it as easy and simple as possible, and then just fucking burn all the GPUs, and it works better. So maybe we just need to pursue simplicity, which I guess is even older than machine learning, right? Like pursuing simplicity is actually like that's a thing in physics too, right? Like all the people who sit there and try to think about like theories of everything and like coming up with very, very simple equations that represent the maximum amount of behavior, right? Like I feel like in almost any intellectual pursuit, like there's this kind of tendency to want to do that, and then you're fighting a tendency to want to make things more complicated. So this like kind of like weird duality between the simplest solution always seems to work, but incrementally improving that simple solution always seems to involve additional complexity. It's kind of like this incrementalism versus fundamentalism approach. I'm sure I'm using those words incorrectly. I don't actually know what fundamentalism versus incrementalism means. There's probably formal definitions for that, but okay, let's get back to this paper here. We nearly return to the accuracy we had before while speeding up the model by 22% for images, 27% for videos. These are huge speed ups, to be honest, like especially for just one change, one like model architecture change. Like if you did a bunch of like over-engineered crap for like a specific GPU and you got a 20% speed up, like that makes sense, but 22% speed up for something that doesn't involve like some CUDA kernel or some hardware specific change is pretty impressive. At this point, the only pooling layers that remain are for Q at the stage transitions and for KV pooling in the first two stages. Okay, so they actually don't have pooling for the key and the values in the later stages. So I've said this many times, and I apologize because many of my videos are probably repetitive, but in an Andrei Karpathy talk, he basically explained the Q, K, and the V as the queries are the things that I want, the keys are the things that I have, and then the values are the things that I want to communicate. Okay? So in the beginning stages, you're pooling the Q, which means you're pooling the things that I want. And why would that be useful in the beginning? It's because at the lower level, everything is more texture, right? So think about it. If you have this picture of a dog, the query, right, the Q matrix is probably things like this is a furry texture. I would like to know if other things are furry texture, right? But like, think about how many times that is repeated. There's like a million different, not a million, but like there's a huge amount of tokens here that are basically all repeating that same exact message of like, hey, I am fur. I want to see if there's other fur. Hey, I am fur. I want to see if there's other fur. Hey, I am fur. I want to see if there's other fur, right? So it makes sense that you kind of want to pool the cues at the beginning because there's probably more repeated stuff in that cue. I don't mean like actually repeated, but I mean like the kind of semantic kind of like hand waviness of like what is in that cue. I feel like it's more repeated at the beginning because at these low level features, it's just things like texture, which tend to be very similar, right? You have whole areas where it's all fur and then whole areas where it's all sky. And then KV pooling in the first two stages. So you only want to pool KV in the first two stages. Why would you want to pool K in the value? Maybe for the same reason. I don't know. Do you guys have better intuition on this? silly analogy about keeping architecture general. It's like trying to teach someone how to swim as fast as possible, making them use inflatable armbands. Armbands help in the short term, but doesn't scale well by getting them better at swimming. I like that, you know. You end up in the local minima, you know, by having all these extra little bells and whistles. All right, removing overlap. The remaining max pool layers still have a kernel size of 3 by 3, necessitating the use of separate and pad trick. So, I mean, like, why 3 by 3, dude? Fuck the 3 by 3 size. Like, make everything in 2s, and then you don't have to worry about these, like, the padding, right? It's like, why have an odd number? Like, that odd number 3 is just so gross. Like, make everything 2, 4, 8, 16, 32, like, I don't know, just little... The odd numbers are just, this does not make me happy. However, we can avoid this problem if we just do not let these max pool kernels overlap. That is, if we set the kernel size equal to the stride, we can use sparse MAE training without the separate and pad trick. All right, so just make sure all your little kernel sizes match the exact size of whatever this like mask unit that they're proposing, and all of it is based on basically 224 by 224, which is the size of the images. This speeds up the model by 20% and 12% while increasing accuracy, likely due to not having to pad. So literally just not having to pad is the majority of the performance, right? So they said up here 22% speed up for images. 20% of that speed up, which is over 90% of that speed up, just comes from setting the kernel size so you don't have to do this padding. So, I mean, that's big. MVIT adds a residual connection in the attention layer between the cue and the output to assist in learning its pooling attention. Between the attention layer, between cue and the output. So, if you actually look at the attention operation... So where's the attention? Give me the equation. This is not the equation. Images. Here it is. So the attention operation, right? You can think of it as a function that uses 3 values here, the queries, the keys, and the values. But the queries and the keys get multiplied together, and then those are used basically as weights for the values, right? So whenever there's a high agreement between the queries, which is the things that I want, and the keys, which is the things that I have, then that high agreement is going to result in the thing I want to communicate, or the thing I have to communicate, that's going to get passed through. Versus if there's some specific cue or part of the cue, which is here's the things that I want, and it doesn't. Basically, whenever I say high activation, low activation, I mean basically like there's an agreement, like the specific Q vector and the specific K vector, like whenever you dot product them together, they make a number that's very high, versus if they're unrelated vectors, right, the dot product leads nowhere, right? It's not exactly a dot product, this is just basically a matrix multiply, but I'm coming from the angle of the intuition of the Q is things that I want, K is things that I have, and then V is what I'm going to communicate to the next layer. But okay, with that aside, the Q and the K will get multiplied, and then you do this V. So what they're saying here is that they're adding a residual connection in the attention layer between the Q and the output. So I guess before the Q, they have a residual connection that goes up beyond the output, right? So if this is the actual attention, the way it looks like in this little block diagram, right? So it sounds like they have a skip connection that goes basically from here and then goes up here. So that's what I'm understanding here, but I don't know, they don't have a diagram, so it's hard to tell. However, so far we've minimized the number of layers, making attention easier to learn, thus we can safely remove it. Okay, so actually, never mind, take back what I said, because they don't even use it. So this little skip connection that they added in the original MVIT V2 paper, they basically just got rid of it, and it didn't seem to matter. So there you go. Mask unit attention. At this point, the only specialized module left is pooling attention. Pooling Q is necessary to maintain a hierarchical model, but KV pooling is only there to reduce the size of the attention matrix in the first two stages. Yeah, so the main reason that people do pooling is just to reduce the size of something in order to be able to compute more efficiently and faster, right? Your K and your V matrices are going to be pretty huge, so if you can reduce them with a pooling operation, shit's going to be much faster. So that's the reason people do pooling, right? It's like, if you didn't have to do pooling, you wouldn't want to do pooling, but you do pooling because or else everything would just be way too big. We can remove this outright, but it would considerably increase the computation cost of the network. Instead, if we replace it with an implementationally trivial alternative, local attention with a mask unit. What? During MAE pre-training, we also have to separate out mask units at the start of the network. Thus, the tokens are already neatly grouped by units once they arrive at the attention. We can then simply perform local attention within these units with no overhead. While this mask unit attention is local instead of global, like pooling attention, K and V were only pooled in the first two stages where global attention wasn't as useful. Thus, as shown in tab 1, this change has no impact on accuracy but increases throughput by a lot, up to 32% on video. So, kind of what's going on here is that whenever you're actually training things on a GPU, right, the GPU has like an actual core, right? It has cores which are actually performing the operations, right? So you can think of it like there's the actual machine that is actually performing the math, and then there's what's called memory, which is where you're storing the values, right? So the most expensive thing in a GPU is taking things out of the memory and putting things into the memory, right? Usually the actual machine that is actually performing, right, the cores that are actually sitting there actually doing the matrix multiplies, that's not making it. That used to be what was the bottleneck, but it's not the bottleneck anymore. Those things can just run all day, right? Nowadays, the problem is that the thing that constantly sits there and does that matrix multiply, it's actually sitting there idly waiting for these memory addresses to basically be changed with new values, right? So what they're saying is that because they were doing this mask unit, right, somewhere inside the memory registers of this GPU, they already have all these tokens grouped into these units into these mask units, right? So if they wanted to do a different operation, they would have to basically take all of those out of the memory, put in all of the new things that they want to do their new operation on, perform the operation, get those out, and then put the mask units back into the memory registers. So this trick that they're referring to here is basically saying, okay, well, let's not do it. Let's do mask unit local attention instead of pooling attention. And by doing that, we don't have to shift out what's in these memory registers of this GPU, which will make it much faster, right? So they're saving these kind of operations where they have to change what's sitting there in the memory that gets operated on by the GPU cores. All the numbers they give on percent speed up seem very kernel compiler op dependent. Like, I'm sure they could have created better kernels that could have done padding without such a performance hit. This part was very interesting. Never occurred to me that you could have different number of queries and keys. I think they have 4 times more keys than queries when using queue pooling in Hiera. Yeah, so if you're only pooling the queues, you're going to have a different... Actually, wait, let me see. Note that mask unit attention is distinct from window attention because it adapts the window size to the size of the mask unit at the current resolution. Window attention would have a fixed size throughout the network, which would leak into deleted tokens after a downsample. Window attention would leak into deleted units after the next stage. Mask unit attention always attends within visible units. Window attention performs local attention with a fixed window size, right? So actually, earlier I was saying at some point you're going to have to choose what the window here is for this local attention. So that's a hyperparameter, but they're actually saying that we don't have to do that because we're not using a specific window size. We're doing this mask unit attention. Performs local attention within individual mask units. no matter their size. And I think like the way they say this sounds better than it actually is. So I mean, another way to interpret this is that we don't have to worry about a fixed size, a window size that is fixed throughout the training and that maybe potentially doesn't overlap correctly with the next stage. Our window size is based on the size of the mask unit, which makes everything work out nicely because the mask unit is chosen such that it fits nicely with the size of the patches and the size of the image and the level of hierarchy that you're currently at. So it's like, just like the more I read this paper, the more I realize that it's like they're basically they're realizing that any kind of padding, any kind of like dimension mismatch in this kind of computational graph is very expensive, right? Because you have to do the padding, and then you're going to have to load new things onto the memory, take things out of the memory. So by creating this kind of mask unit and then basing all these different processes on the size of that mask unit, you basically get a huge efficiency and speed up. Ankit with a random, I like the random question, Ankit. What's your view on the Vision Pro? Do you guys want to do a little Vision Pro side step here? So the Vision Pro is the VR headset that Apple announced. Obviously, it's very expensive. It has 4K in each eye, which is the highest resolution. I think there's a Pimax is another VR headset that has a very high resolution, but obviously the Apple one is going to be better because they have really good screen technology. I think that from what I heard, all the demos that people had were sitting down, so I'd be curious whether or not the tracking is good. Supposedly the hand tracking is good, but the hand tracking is also good on the Oculus. I have the Quest Pro here in my house. I also think that Apple, the development experience is still to be determined. They supposedly are partnering with Unity, but they aren't partnering with Unreal Engine, and Quest partners with both Unity and Unreal Engine, so that could potentially be an advantage there. Of course, there's the battery pack that's external. I don't know. I think that it's a good thing for the VR community. I think actually Apple releasing a VR headset is a good thing for Meta. I know people are saying that it's a bad thing, but I think it's a good thing. I think that as soon as you have multiple competitors, they can kind of steal things from each other, right? So any feature that comes in the Apple Pro, you can expect it to come out in the Quest headsets, and then any feature that comes out in the Quest headsets, you can expect it to eventually come out in the Apple, and then we win as customers because the stuff gets better faster. So I don't know. I've done some VR stuff. I'm definitely not like a VR expert, but I'm definitely excited, and I'm looking forward to a future where I don't have to have these screens and this mouse and all this crap, and basically all my compute can fit in a single headset that I put on my head. So more competition, more options. Yeah. I could talk like all day about VR. Maybe we do like a specific VR stream, because we still got to get through this paper. But thanks for asking the question, Ankit. The result of these changes is an extremely simple and efficient model, which we denote Hiera. Hiera is 2.4 times faster on images, 5.1 times faster on video than the MVIT2 we started, and is more accurate because of MAE. Furthermore, because Hiera supports sparse pre-training, the results are extremely fast to obtain. We obtain superior accuracy on images, and it's 3 times faster to train. So this is inference time, and this is training time. We report 80% using a cut-down version and double the KV stride in the first 3 stages. Hiera L obtains 85% in 800 pre-trained epochs while being 2.1 times faster. All benchmarks on this paper are on an A100 with floating point 16. I don't know about most useful. I think that if you look at the quantization papers, I feel like you have to be using 4-bit or 8-bit. I've even seen 2-bit. I saw that. I don't know when I saw this, but 2-bit quantization. Yeah, dude, like look at this shit. 2-bit quantization. Like we're getting crazy at this point. Like what do you even how do you fit like a floating point number into 2 bits, right? Like that, the fact that 2-bit quantization even works is absolutely insane. But yeah, floating point 16 is pretty noob from these meta researchers here. I would have liked to see the 8-bit or the 4-bit. Measured in half precision, A100 days. So training obviously is at 16 precision, but inference is what I'm talking about. Inference at the 4 and 8-bit. Measured in half precision, A100 days. Half precision here because normally the precision was usually 32-bit is kind of like has always been the standard, but then half precision is 16-bit, which is 16 is 1/2 of 32. Our Hiera is significantly faster to train than the MIT V2 due to being more efficient and benefiting from sparse pre-training. 300 epochs, so 1 epoch of ImageNet 1K is basically you go through the entire dataset 1 time. 300 means you go through the entire dataset 300 times. While mask ViT use 400, followed by 50 epochs of fine-tuning. Node Hiera at 200 epochs of pre-training already performs MIT V2L supervised on video, making it 5.6 times faster. Okay, so what do they mean by pre-train and fine-tune? So pre-training refers to this task here that they're doing, this masked task where you're basically given an image, just try to predict the missing tokens, and then you basically build up a very good visual representation in this final layer here. But then fine-tuning is whenever you basically throw away this decoder and then you just put a classification head right here, and then you train it in a supervised manner on the ImageNet 1K classification task. So that's the difference between the pre-training and the fine-tuning here. So look at this, which is actually really cool. I love how you can visually see the difference here, right? If you were to take this model architecture and only train it in a supervised manner on this classification task, this is where you get. Versus look at the amount of pre-training and the amount of fine-tuning, and this is going to perform way better, right? So the fact that you can pre-train and then fine-tune, and that works better than just supervised learning, is, to me, that's still one of the like miracles of machine learning, is that it actually works, right? That you can have a pre-training task that results in visual representations that are actually good for a downstream task such as classification. But I guess that's not really the point of what they were trying to show here. What they were trying to show here is that obviously the MVIT V2L is much slower to train than the Hiera L. What they want you to see here is the size of this bar compared to this bar, and just how much smaller this bar is. Unkit or ARKit? I don't know if it's Unkit or Ankit or Ankit, or I'm sorry if I'm pronouncing your name wrong. No collab was unexpected. Yeah, I mean, I've used both. So whenever I did my synthetic data startup, I built the entire pipeline like multiple times. I built it on top of Unity, I built it on top of Unreal, and then I also built it in Blender in Python. Unreal is way harder to use than Unity, but it's also way more powerful. So it's actually unknown. I couldn't tell you whether Unity is going to win the race or whether Unreal is going to win the race or whether even Roblox is going to win the race, but I think that you should be able to support. Like, to me, if you're making a VR headset is fundamentally a platform, right? So you want to support everything. You want to support all the different game engines. You want to support all the different possible ways of developing apps and products for your platform. So to me, Meta is more aware of that. You know, they know that they need to support everything. They need to be able to support Unreal and Unity, but Apple is being elitist, you know, and they're being very picky, and they're saying, okay, well, you can only develop with Unity, right? And generally when you do that kind of preferential treatment for one way of doing things versus another way of doing things, it leads to a less active developer community, which leads to less apps and eventually leads to a worse product offering. So we'll see what happens. We'll see if it matters, and maybe it doesn't. You know, because what Apple has is the brand value. The brand value of Apple is huge, right? Like, people will wear Apple products because it's almost like jewelry. It's like a status symbol, you know? So I think that's kind of something that's difficult to really measure the impact of, and it could end up being a very important part of who ends up winning the VR race. I've used C#, dude. C# is great. It's like objectively terrible, you know, like C# is like a garbage language, but it's basically like you feel like you're writing C++, but really you're writing Python. So you can pretend that you're writing C++ when you're really writing Python, aka C#. Number of channels, number of blocks, and number of heads. So obviously whenever you see attention mechanisms, there's multiple heads to the attention mechanism. Channel width, number of Hiera blocks, and the heads in each block, respectively. Flops are measured with a 224 by 224 input. The resolutions at each of the different stages are 56, 28, 14, and 7. So I think this resolution also changes the size of this mask unit that they introduced. So here are all the different sizes of the models. You have 673 million parameters in the biggest one, and then you have 28 million parameters in the tiny one. The final dimension of the visual representation in the biggest version is 2048 and 768 in the small one. Ablations. So kind of weird. I feel like you don't need an ablation study. If your model architecture is simple enough, then ablation studies are doesn't make any sense. Like, what are you ablating? There's only one thing. We ablate using our large model. We evaluate performance. All metrics are top 1 accuracies using standard evaluation protocols. Use tokens from the last block of the encoder as the input to the decoder. Being hierarchical permits more flexibility. We use multi-scale information by fusing representations from all stages, which brings large gains. Oh, okay. So up here, right? I keep saying that this very last layer is the visual representation that you would use for a ImageNet classification task once you're actually doing the fine-tuning. But what they just said there, what they're saying is that they actually have residual connections which bring up features from previous layers, right? So the very last vector here, this embedding, this feature representation, this compressed form of the original input image, which is the whole point of your encoder, is creating a compressed form of that image. They're saying that rather than just using the last block, they're going to basically pass in information from previous layers as well. So that's kind of interesting. Masking ratio. We find video to require a much higher masking ratio than images, suggesting higher information redundancy. I mean, that makes sense. You know, videos are basically the same frame over and over again, so you don't really need all of it. In fact, most video encoding standards are based around this assumption that you only need to keep certain frames, and then you can basically, like H264 codec. Yeah, so there's all these different video encoding standard or kind of algorithms that these are hard-coded ones. These are not based on deep learning, but basically you only store specific frames, and then you store everything else as a modification of those keyframes, right? But yeah, the fact that that works kind of adds evidence to this claim that video has higher information redundancy, which obviously is obvious if you actually think about it for a second. We observe a similar trend with optimal masking ratios of 0.6 and 0.9. The optimal ratio for images is slightly lower than the 0.75, and they actually benefit by using a lower ratio because it's going to improve the speed, right? So they actually want to make this ratio as small as possible, or not as small, but they want to mask out as much of the image as possible because it makes their whole pipeline faster. We expect this is due to increased difficulty of the pretext task when you change the mask unit size. they actually find 0.95 to work optimally. With our increased task difficulty, 0.9 works out to be the best. We find that both Pixel and Hog histogram of gradients. Is that what they mean by Hog here? So histogram of gradients is a very old computer vision technique. It's like a hand-designed feature. Result in strong performance. Hog targets result in slightly better performance for the default number of pre-training. We found that with longer training, Hog targets achieve the same performance as Pixel targets, but slightly worse for images. I don't think this is histogram of gradients. Is this histogram of gradients? Yeah, histogram of gradients. Okay, so that's a very ancient paper that they referenced there. I was like sitting there, I was like, is it actually fucking Hog? Like, am I seeing that? Drop path rate. The original MAE pre-training recipes explicitly do not use a drop path during pre-training, instead of opting to only do so while fine-tuning. However, our hierarchical Hiera L has twice the depth of a ViT L model, 48. While each layer individually has lower parameter count, due to the sheer depth of Hiera, there could be a significant benefit from drop path. We ablate applying drop path during pre-training. Fine-tuning employs drop path by default and finds significant gains. This is surprising because it means that without drop path, Hiera can overfit to the MAE task. Huh. You can overfit a pre-training task? That's fucking crazy. That almost doesn't make any fucking sense. Isn't this a huge data set? How could you overfit to a task as generic as masked token prediction if your data set is absolutely huge? Like, I can understand overfitting to like a classification task, but this is kind of crazy. We find that a significant benefit from a deeper decoder than previous work brings the decoder for video in line with images. Pre-training schedules. Several masked image modeling approaches have found benefit from longer pre-training schedules, often using up to 1600 epochs. We observe that the same trend, increasing about 0.5% over 400 epochs. Hiera is a more efficient learning. It can learn faster. Even with only 800, outperforms all the previous state-of-the-arts. But basically what they're suggesting is that you could keep training this and it would probably keep pushing the state-of-the-art. All right, so here is the different ablations for the different things here. So you got the multi-scale, whether or not it's multi-scale, get a little bit of a performance boost there. Mask ratio. Here the multi-scale is whether or not the final visual representation includes basically these is concatenated with previous layers. I think that's what they mean there. Mask ratio, this is the how much of the image is basically empty, so 0.5, 0.6, 0.7. There's a U-shaped kind of behavior here where if the mask ratio is too low, you're not going to get as good performance. If the mask ratio is too high, you're not going to get as good performance. So finding that magical, perfectly lukewarm soup of 0.6 for image and 0.9 for video. Pixel versus histogram of gradients here. 85, 86. This doesn't seem to make much of a difference. Drop path also doesn't really seem to make much of a difference. Like, every single one of these ablations is like, none of these are that crazy. Like, every single one of these, you're talking about 0.1% here. Like, I don't think any of these are significant. 86.1 versus 85.8. Like, I don't know. That seems about the same to me. Damn, dude, they trained this for 32,000 epochs? That's fucking crazy. They must be compensating for not having done almost enough ablations in the MVIT2 V2 paper. Almost all the ideas they introduced in that paper seem to do more harm than good. Apple also work hard for making sure that their products remain difficult to repair. Yeah. Apple loves to, it's kind of like cars, right? I remember someone told me once that most car companies, they make more money on the like maintenance and like repair of cars than they actually do when they sell the cars. It's kind of like printers where like they're making most of their money on the ink. But I feel like maybe there's something to that. Like, I don't have an iPhone, but I assume that when your iPhone is broken, you can't even do anything. You have to go to the store and give it to them, and then they probably charge you a shit ton of money to repair the iPhone. So maybe that's kind of like a huge revenue driver. So they want to make sure to keep that model alive with the headsets. Okay, so here they're going to be comparing Hiera with the ViT V2, and they're going to be doing it on K40. This is the kinetics data set. It's basically video classification. Let me see if I can actually... K400 kinetics 400. Let's actually see what this data set looks like. So this is what it looks like. It's basically this kind of like shitty, grainy video of like stretching leg, and it's like... How many frames is it? Each clip lasts around 10 seconds and is taken from a different YouTube video. So it's like 10-second clips of YouTube, and you have to classify. But you can see here the usage. So if you look at this plot, it is getting more popular over time. And you can compare it to some of the other things. So for example, this one here, HMD, UCF 101, so you can kind of compare which benchmarks are being used in papers. All right, so this entire paragraph of crap is probably just telling you exactly what's in these figures here. We have 85 versus 81. We have 87 versus 86. These are different sizes. So this is the big, large, and huge. Yeah, look at this. 51 million parameters versus 80 and get 84. 87 million parameters and get 81. So less parameters, better performance. Pre-training, whether you're pre-training on SSV2 or pre-training on K400. Okay, I mean, this number is terrible. VITL supervised on K400, 55 versus 75. ImageNet 21K. Yeah, I don't know. I mean, they're better, but they're only really comparing against MVIT V2L. So, I mean, it's difficult to really compare when the only thing they're comparing to is a previous version of their work, you know? I wish they would have compared to other vision transformers and other models here, but they really only compare against this one. So it's hard to tell. Image results. We first evaluate performance on ImageNet 1K and then transfer to other image recognition, detection, and segmentation tasks. We perform system-level comparison, trained with MAE to relevant prior work. We observed that the supervised MVIT V2 baselines are already quite strong, and MVIT V2BL... What the fuck is MVIT V2BL? It's MVIT version 2 big L. What? Better than several approaches that use pre-training. This showcases the significant benefits that convolution give in the supervised setting. Yeah, so they're basically saying that if you're only going to be doing supervised learning, right? If you're not doing any fine-tuning, then maybe the convolutions and the kind of spatial bias that they introduce actually results in better performance. But if you're only doing supervised learning from scratch, what the fuck are you doing? It's 2023. You should be using a pre-trained model. Hiera ST remarkably strong performance in a scale regime where convolutions have historically dominated, consistent with our core premise that good spatial biases can be learned. This is kind of almost like a different version of the bitter lesson, right? The bitter lesson is more about computation or scale in the sense of computation and data is key, but here they're actually saying that you can actually learn the biases and priors themselves rather than actually trying to put them into the model, which is kind of existential, I think, for researchers, because a lot of what researchers do is trying to figure out good biases and good priors to constrain the learning and optimization process of some kind of model. So if it turns out that you're just hurting rather than helping, what the fuck are we even doing? Our simple hierarchical vision transformer outperforms state-of-the-art on images and far exceeds prior work in video. Extremely loose use of far exceeds. Our model significantly outperforms a 2022 or a 2003 paper that we found that's somewhat similar. Reaches an accuracy of 86%, significant gain. Transfer learning. We perform transfer learning on downstream classification, detection, and segmentation. So, iNaturalist, places. These are different classification data sets. Coco, another classification, also detection, also segmentation data set. Average precision for box, and then average precision for mask. So mask is the segmentation task, and then box is the object detection, so you're bounding boxes. Okay, this is more what I want, right? So here they're actually finally comparing to other models here. So you have the ViT, you have the Swin transformer. Yeah, and this kind of paints a different picture, right? Like 81%, 82%. 83%, 83%, 83%, 85%. Like, it's really not that much of a performance improvement. You are getting, like, this is nice, like this part here, right? The fact that you get slightly better performance, but you get a smaller model here, 50 million versus 35 million. So I guess there's something there, but we're not talking like significantly exceeds performance, right? Like these aren't like blowing things out of the water. These are like kind of on par. It's just the size that is impressive, right? You have 214 million with 86 versus 85 at 304 million. We de-emphasize approaches using extra data and indicate the source of the extra data. Okay, so here they're pre-training with this masked autoencoding task, but here, I guess in this ViTL, they're also using DALL-E. You can use diffusion models as basically data generators, right? Because a diffusion model, in a sense, is basically just the entire data set compressed into the weights of a model. Feature pyramid network. This is another old one. Demonstrates strong scaling behavior when compared to models. Plus 1.8 higher. Compared to state of the art, our higher model achieves comparable results while having faster inference and a lower operation count. Yeah, I would say this is more the correct way to talk about what this paper achieves. To me, it's not like they're blowing the performance out of the water. What they're doing is they're creating a model architecture that is significantly faster and significantly cheaper to compute and has slightly better results. So to me, it's not a win in the performance. It's a win in the faster inference and lower operation count. Okay, in this work, we create a simple hierarchical vision transformer, taking an existing one and removing all of its bells and whistles while supplying the model with a spatial bias through MAE pre-training. So, I mean, at least they're honest here that what they're doing is a form of spatial bias. It's not like they got rid of the spatial bias. They just found a better way of adding the spatial bias. Hiera is more effective than current work on image recognition tasks and surpasses the state-of-the-art on video tasks. We hope Hiera can allow future work to do more faster. This sounds like corporate jargon right here. Some corporate person came up with this for sure. This little last sentence here. That doesn't sound like an engineer came up with that. A mask unit for course video corresponds to a block of 2 frames by 32 by 32. Each token in Hiera on video corresponds to 2 frames. Since the mask unit also pans 2 frames. 2 frames here is like frames of the video, not... That's what they mean there. The window sizes for the mask unit attention do not change for the video, so they're still using this 8x8, then 4x4. Just the mask unit. We use learned spatial position embeddings for images. Wait, what? So, I mean, earlier they said they were using absolute position embeddings, and now they're using learned position embeddings? Oh, okay. So the learned position embeddings is only for the video, but the image embeddings just use the images only use the absolute position embeddings. The rest of the encoder is completely agnostic to spatio-temporal structure. I think separable spatio-temporal means that it's basically the position embedding for the position of the patch within the image. That's the spatial part, and then the position embedding for the where that frame is in the whole 10-second clip, right? For this Kinetics 400 dataset. So I think the word separable there refers to the fact that they're not basically mashed together into one position embedding that represents both the space and the time of that patch in the video. They're probably just concatenated. That would be my guess. We remove the queue pooling before the last stage. This is done so that MAE settings from work using ViT also accounts for Hiera with minimal modifications. This introduces little extra computation as stage 4 is small. If desired by design, pre-training with Hiera can also work without removal of query pooling during pre-training. So this is the pooling in the query matrices, since a mask unit of 1x8x8 would correspond to 1 distinct token. Okay, so these are the different video experiments. The positional embeddings are always learned absolute positional embeddings, I think. Yeah, we need like a positional embeddings like summary paper. You know? I feel like I'm gonna try to do that. I feel like next week I'm gonna try to find some kind of positional embeddings paper. Because I think like that's like a whole area of research that like has kind of like exploded, and there's like a million different positional embedding variants at this point. But I feel like I need to improve my intuition. There was a nice blog that I remember reading. This one, I think it's this one. Yeah, I think this might have been it. But I've seen some good explanations of what positional embeddings are actually doing, or like what, because it's basically like this weird sine cosine thing. Yeah. So the positional encoding, this is what it actually would look like, right? But I think it's the type of thing where I think I understand what it is, but I don't actually understand what it is. You know what I'm saying? So I'd love to, I think it's about time we go back and actually really try to understand deeply what the fuck a positional embedding actually is, or absolute positional embedding versus all the other variants of those. Human action localization. ROI features. This looks like mask RCNN. ROI means region of interest. We report the pre-training and fine-tuning settings, transfer learning. Ooh, okay, look at this. Here are all the different parameters that they're using. So they have a pretty aggressive weight decay here. Cosine decay for the learning rate. Schedule. They got warm-up epochs. They're still using data augmentation, so they're horizontal flipping like this, and then cropping. These are big batch sizes, so of course they're training on these big A100 server racks. So, I mean, that's consistent, that makes sense. This is basically the dropout, but its drop path is a little bit more complicated. Number of heads, like, people generally just keep it at 8. It's like this magic number that has kind of emerged. They really like this cosine learning rate schedule. Here you have the cut, mix, and mix up. This is the data augmentation technique that we were seeing yesterday in the fMRI paper. They also used this mix up technique. Okay. We use an NVIDIA A100 40 gigabyte GPU. Look at this, dude. Even within Meta AI research, they're not even using PyTorch 2. They're using PyTorch v1.12 with CUDA 11.4. Note that we did not use flash attention or any other attention speed up mechanism, though they can be used to further increase speed. Yeah, you could have also increased speed with quantization. We use half precision to run speed benchmarking. Could have done it in 4-bit. How much faster would it have been? That would have been pretty fucking cool. We measured the speed of the forward-backward pass on a single GPU and extrapolated the total training time according to the size of the dataset and the number of training epochs, ignoring data loading and communication overheads. This is literally one of the biggest overheads, so I don't know if you can just ignore that. That's like literally the hardest part of training in a giant distributed rig is the fucking data loading and communication overhead. We report the image benchmarking on NVIDIA A100s with floating point 16s. From scratch supervised training. This is what they were doing as a baseline, where rather than doing this pre-training and then fine-tuning, they basically just trained this model architecture from scratch with the supervised task of just classification, image label, image label, image label, right? But that's going to kind of result in crap. And that's, I think, what they're trying to say here is that if you don't have this MAE task, right, which in a way is teaching the spatial bias, you're not going to have that spatial bias so that your model architecture is going to perform shit on this supervised training task. We do not claim that these models are unnecessary in general. In fact, here we intend to show the opposite. The reason these spatial biases were necessary in the first place is because they were required when training a vision transformer from scratch with classification. That's a big... I just think, like, to me, this is the biggest kind of intuition I've learned from this entire paper, is that the task itself introduces biases, and you can introduce the biases that you need for a problem. Like in vision, you obviously need some form of a spatial bias. You can introduce that in the task, in the pre-training task itself, rather than by introducing it in the model architecture. And I think if you can take that high-level idea and apply it to other domains, there's probably a bunch of low-hanging fruit in the research world for taking this idea and applying it to diffusion models, applying it to language, applying it to I don't know, graph neural networks. Are graph neural networks still a thing? But I think this is powerful. I think this is a very powerful idea, IMO. We see the opposite trend as when training a strong pretext task. The bells and whistles are unnecessary when training in a classical supervised setting. This reiterates the fact that by training with MAE, we are replacing the need to explicitly build spatial biases into the network architecture itself. Note that this also has ramifications for downstream tasks. While prior specialized vision transformers or SWIN act like convnets, Hiera acts like a ViT. I don't know what the fuck that means, but we recommend using transformer-based solutions for downstream tasks such as ViT det and for detection instead of mask RCNN. Yeah, I mean, gotta be using transformers. And then we just got the references. Okay, nice little, cute little short paper there. I think Nope paper was fire. Is that a paper that I talked about? What is this? Oh, this is the no positional embeddings paper. Dude, I never ended up reading that. Was it actually good? I didn't read it. I just like posted it without reading it, so I guess I was I don't know, you tell me, Nisio. If it was good, I can read it. I just assumed that it might have been crap, so I just didn't read it, but maybe I fucked up. Maybe I should have read it. Okay. Let's summarize this paper so we can all go work on actual work instead of reading papers. But all right, so today we read Hiera, Hierarchical Vision Transformer. This was a paper out of Meta AI Research. Basically, they trained a simpler version of the vision transformer. They removed a bunch of different bells and whistles and tricks that people were adding to vision transformers in order to kind of like introduce spatial bias into the transformer. Right? But what they figured out is that by simply doing a masked autoencoding pre-training task, that is a way of introducing spatial bias that is sufficient to learn a good visual representation, which then ends up being useful for classification and so on. And if it's useful for classification and detection, it's probably useful for whatever the fuck you want to use it for. So one of the key kind of in addition to that, one of the key things that this paper did is that they achieved significant speed in the inference and in the training, and they did that by being very clever and careful about the size of the pooling operations, the size of these kernels that they use for pooling and for conv and stuff like that, and the token sizes. And they introduced this concept of a mask unit, which is basically just kind of a superset of tokens. Like you have, like here it's a 4x4 grid of tokens, represents one mask unit, and the actual size of the mask unit changes over the course of the model architecture. So at the beginning you have tokens that are mask units that are 8x8 pixels, and then at the end you have mask units that are basically 1 pixel at a size, or 1 pixel sized. Although it's at the very end, it's not going to be a pixel anymore, so hand wave that. They do use position embeddings. What else? It's faster and it performs better. So I don't know. That's kind of the summary. They have the GitHub up. Unfortunately, you're not going to be able to use this for your cool startup idea because it's a non-commercial license, but you can use this for your research. And the models are not yet posted, so unfortunately you're not going to be able to download a pre-trained model, but they said that it trains much faster, so if you have an A100 in your lab, maybe you can just train one of these yourself from scratch. It actually seemed that with the dataset that they were using to pre-train this was not actually that big. I think they pre-trained it on Kinetics 400, right? So I'm pretty sure if you take this and pre-train it on Leon this one, Leon 5B. You might even be able to push the state of the art. So this is like a huge data set that's commonly used for huge transformers. .5 terabytes, 6.2 terabytes. But yeah, that's it. Cool little paper. I like it. To me, I love the fact that simplicity is resulting in performance improvement and speed. You know, I want the world to get easier to understand as I get older. I don't want it to get harder to understand. So I think this is a big win. Not much details, but interesting insight. Yeah. Simple concept. Thanks, Nisio, Ankit, everybody else, Lucas, who made comments. Thank you for watching. You guys have a great day. See you tomorrow. I think tomorrow is just going to be a casual coding and hanging out. If you guys just want to sit around and code and hang out, probably just going to code on the Discord bot, but we'll see. Maybe we code on some other crap. But thanks for watching. Likes and subscribe. See you guys later.